Hello, in this video I will demonstrate the analysis of RAS MAPK pathway mutations on the activity of different pathways and on overall survival in different cancers. So first, we're gonna start by populating the graph with mutations, somatic mutations in different RAS and RAF genes. So NRAS, HRAS, KRAS, BRAF, and let's just add EGFR as well. Say add. Now we have these 5 genes. When you look at them individually, you can see the distribution, the frequencies of their mutations at different cancers. But another thing that you can do in SEMA is by looking at them collectively. So to look at these the collective, basically in mutations in the whole RAS MAPK pathway, instead of looking at them individually, you just combine these variables into one by using this function here. So here you can combine these categorical variables. So mutations are categorical variables, right? So they're either wild type or mutant. So you can combine them into another categorical variable, which we're gonna name RAS MAPK. In the first category, so basically where these are going to be the samples that have none of these mutations, we're going to call them wild type, and those samples that have mutations in any one of these genes, we're going to call them mutants, and we're going to change these to mutants. Now basically, if any of these are satisfied, if a sample has mutations in any one of these genes, it's going to be put in the category mut. If none of these are true, or if the sample is wild type for all these genes, it's going to be wild type. Click OK, and now we have the new variable RAS MAPK node, which shows the mutations in the whole pathway. This is the distribution, and now let's analyze their effect on MEK phosphorylation. Let's do individually first. Click evaluate. Analyze z-scores, and this is across all cancers. NRAS leads to higher MEK phosphorylation melanomas in stomach cancers and in thyroid carcinomas. EGFR mutations do not really affect MEK phosphorylations that much. The z-score of negative 2 and positive 2 correlates to a p-value of roughly 0.05, so none of these really reach that p-value, so it's not really that significant. BRAF mutations are significantly associated with higher phospho-MEK levels in colon, melanoma, and in thyroid carcinomas. KRAS as well in colon and in uterine carcinomas. And HRAS not so much. Now, let's remove these links, and now let's look how when we compare samples that have any of these mutations versus samples that don't have any of these mutations. So now, would we see now a stronger effect on MEK phosphorylations? And yes, indeed. So now this is way more consistent than looking at each of them alone, right? So because now we see a consistent positive effect of cumulative mutations in these genes in most cancers here, in colon, in head and neck, in lung, in ovarian, in melanomas, in thyroid carcinomas, thymomas, and in uterine carcinomas. Now let's just remove these because this is a better representation of the effect. Let's analyze its effect on clinical survival. So only in low-grade gliomas we have an effect of RAS-MAPK pathway mutations on survival, and actually a little bit in melanomas as well. Let's look at low-grade gliomas. Oh yeah, this is obviously highly significant. Okay, now it's not just mutations in the RAS-MAPK pathway. We also have amplifications of of EGFR that may impact this pathway. NRAS, I believe, is also amplified in some cancers, and BRAF. Now let's see if it's true, if they are really amplified. Yeah, so anything the above 0 is basically frequent copy number gain in these cases. In melanomas, in GBM, quite frequent amplifications in BRAF are observed in kidney papillary carcinomas, in ovarian, in melanomas as well. Let's look at NRAS. NRAS not so much. EGFR, as you would expect in GBM, it's quite frequently amplified. Now, it helps to binarize these variables. Instead of looking at these variables as continuous variables, let's binarize them into amplified versus non-amplified. So for that, we'll be using this function here, binarize. So this function will binarize any continuous variable. So the continuous variable can be mRNA expression or copy number variation. It makes most sense in binarizing copy number variation. So let's just binarize it to, let's say, wild type, and let's put a cutoff of, let's say, 0.5, and gain, copy gain. Now, the new variable is a categorical variable, and so instead of box plots, we see this plot here, where NRAS is frequently copy number. We see copy number gains in melanomas and in ovarian carcinomas. Let's binarize EGFR similarly. Same cutoff, and yeah, in GBM, as you would expect, it's very high amplification rates. Now let's do the same thing for BRAF. Yeah, so it's frequently amplified in GBMs, in kidney papillary carcinomas, in ovarian cancer, in melanomas. Now let's see how these affect MAP kinase levels. Evaluate. First, let's look at NRAS. Z-scores, please. So, in melanomas, not so much. And overall, we don't really see that strong of an effect of amplifications on MAC phosphorylation. Of course, here we're controlling for RAS-MAPK pathway mutations. So if this has a stronger effect, and that may confound the effect of these variables. BRAF amplification has, again, not really any effect compared to the mutations and the amplifications in these other genes. EGFR amplifications only have positive effect in bladder cancers, but actually has a negative effect on MAC phosphorylations in GBM, in low-grade gliomas, and in lung. Of course, again, we are controlling for RAS-MAPK pathway mutations. So if we look individually, yes, it is actually true. So whenever you have a gain, you have less. Like for example, in lung cancers, you see this is less actually. The phospho-MAC levels are less. In GBM also, phospho-MAC levels are less. This may be surprising, but this is data. How about if we combine these? Copy number. So looking for copy number gains. Basically, we're going to be looking at them cumulatively. So let's remove these. We're not interested in them anymore. Click on the link. It doesn't look like much changed. In fact, now we have even stronger negative effect on MAC phosphorylation in lung cancers and in GBM, lung squamous and in GBM. Here, so MAC levels really are lower in GBM when there is a gain in these tumors, which might be surprising, but this is data. And again, just to compare this with the somatic mutations, which are always giving higher MAC phospho levels. Let's also look at their effect on survival. Z-scores. So in kidney chromophobia and in low-grade gliomas, the copy number gains in the RAS MAPK pathway genes leads to significantly worse survival, whereas in the somatic mutations, in low-grade gliomas, it leads to significantly worse survival. At least there's a concordance in low-grade gliomas between copy number gains and somatic mutations. So let's add other pathways. How about AKT? Let's remove survival just to make it simpler. There is no consistent effect of MAPK pathway mutation on AKT. Although in thymomas, the copy number changes actually do lead to significantly higher phospho-AKT levels. Let's, just to compare, add mutations in the AKT pathway. So P10, PIK3CA, AKT1, some of the frequent ones. Let's sum them up. Combine them into AKT pathway. So AKT pathway mutations are quite common in uterine carcinomas and in colon cancers. Remove these. And so, this is AKT, this is MAPK. So we're looking at AKT pathway mutations on AKT, phospho-AKT levels, and it is obviously quite consistently high across all the different cancers. AKT pathway mutations affect AKT positively, whereas it has a negative effect in a couple of cancers, but overall there is no consistency. RAS MAPK pathway mutations do not really have that much effect on AKT. Either mutations or copy number changes do not really affect AKT that much. So there you go. So this was again just a kind of improvised analysis of pathway mutations and copy number alterations, and I just wanted to demonstrate how to combine the different nodes together to analyze cumulative distributions and their effect on different biological and molecular parameters.